So let us start the today's discussion with the long channel effect and the short channel effect. First, let us see. So what will be in the long channel effect or what is meant by long channel effect? So long channel effect in the sense now we can consider the cross section of your MOSFET. This will be a gate. This will be the source. This will be the drain. Then this will be your channel. We are considering the N MOSFET. Then we have the another one terminal that is named as bulk terminal. Now we can say this portion is nothing but a L, where L is nothing but the channel length. So now long channel effect. If the length of the channel is greater than 1 micrometer, what are the effects will get happen? So you might have studied in a previous CMOS VLSI, you might have calculated the equations like for all some three regions. So you can operate the MOSFET in three regions. So what are the regions I want? The first one is something you can operate in the cutoff mode, that is cutoff region. The second one is linear region, or I can say as nothing but a resistive region. Then third one is we can say is a saturation region. So as you know the condition for cutoff actually like your VGS. The VGS is nothing but the bias voltage, the voltage applied between the gate and the source. So VGS is less than VT, then that is in, or I can say the VGS is equal to 0 volt. If I'm not applying any voltage or less than the threshold voltage, then the transistor will be in off condition. So that is what we can say it's a cutoff mode. Next, second is linear region. What is the linear region? The linear region is nothing but the VDS is less than VGS minus VTH. This is the condition for linear region. Next, the saturation region. For saturation region, the VDS is greater than or equal to VGS minus VTH. So in this saturation region only, one important thing will get happen. So you might have studied that is nothing but the pinch off. As we know that what is the saturation region, as you are applying more and more the VGS voltage, if it is very greater, automatically what will happen, your the channel will be pinched off. So if the channel is pinched off in the sense, the channel will get reduced. That is why initially I can say the large, this is especially what I'm showing here. It is a long channel effect. This is like this is long effect in the sense I can say with during the saturation region. So your channel will be pinched off. How it will? I think you can recollect what you studied. Like so normally as you know that this will be your depletion region. Correct. So the channel will be pinched off in the drain end. So if the channel is pinched off, only a small amount of current only will flow. Constantly the current will flow over there. Now in the long channel effects, we have two different types of long channel effect is there. That is one is nothing but a channel length modulation. This we are not going to discuss actually. Channel length modulation. The second one is nothing but body effect. The channel length modulation. The channel length modulation is simple. I can say this is what the channel length modulation. Like the channel length modulation parameter will be considered as lambda actually. So whatever you might have studied your ID equation. I hope you remember the ID equation, right? So in the ID equation, actually, what will happen? So from that, just it will be add one parameter will be added the channel length one, because here you can see this whole thing. It's nothing but a total L actually. Correct. So what will be your effective length is nothing but L effective will be effective length. So after the saturation region, we'll get L minus delta L. The delta L is nothing but the how much the channel is like shrinked. That is what I can call it as L minus delta L. So this will consider in the channel length modulation. So now what we'll do, let us study about the important of the body effect parameter. Body effect. The body effect parameter normally will denote as gamma actually. So now, okay. Let us consider same the MOSFET only we need to consider. I hope you might have remember in when you have studied the MOSFET diagram like all like here uh, like a simple I can say let me put a diagram so I think it will be more clear for you. It is equal to 0, then Vg is less than Vth, then your Vs will be is equal to 0. This is source terminal, this is gate terminal. Then you may have the this is the depletion region. Then we have the channels. Okay, this is the channel. Repeat substrate. This will be your bulk. That is bulk voltage will be is equal to 0. So very important here. So when you are studied the VI analysis or the IV analysis, we assume that the bulk and the source of the MOSFET were tied to ground. You can see here the equivalent diagram. If I need to draw, it will be like this. This will be your drain. This is source. This is gate. This will be your bulk light. This is what so and to ground. Now this bulk and the source you can see here both were tied to ground. Then what will happen if the bulk voltage of NMOS drops below the source voltage? What is the meaning that? What will happen if your bulk voltage goes more and more negative? Initially, or I can say always, the bulk voltage must be lower potential or the bulk must be zero. But when it will happen, the VB is less than 0. When it will happen in the sense, so very simple, I can say. So VGS voltage will be is equal to VGB minus VBS actually. So now we can say this will be like a VG minus VB minus VB minus, because as you know that VGB is nothing but the voltage across or the potential difference between the gate and the bulk. So VBS is nothing but the potential difference across the bulk and the source. Now we can see here, if your B voltage goes very, very negative, what is the meaning of that? If your bulk is goes very, very negative means like your source voltage means negative means example you can apply. Let me take example. Okay. So let me take. So as per our condition here, VG should be like less than the threshold voltage. Assume threshold voltage is normally for NMOS transistor 0.6 volt. Okay, so what will be VGS now? VGS is equal to what is the gate voltage? So as I mentioned, less than threshold voltage. So simple, I will take 0.1 volt minus VB. Just initially, I'll consider 0 volt only. VB, I'll consider 0 volt only minus 0, then this also source also will be 0, then VGS voltage is positive, that no problem, nothing will happen. But so Vs is negative. If I put more negative value, say example Vs is negative or less than 0 voltage, if I add, means what is the meaning of that? So if simple, I can say, I'll put a contest. If to understand the effect, like okay, if you need to understand the effect, Vs is equal to 0 and Vd is equal to 0 and Vg is constant, somewhat constant, I can say, somewhat constant, or I can say Vg is less than Vth, so that the depletion region will be formed. Depletion region formed under the gate, but inversion channel does not exist. This is what we shown in the previous figure. So now what we will do, let us go for the condition as like this is the one condition we took, right? So let me take like as VB becomes more negative means VB is very, very less than 0, or I can say the VB is less than source voltage, because the Vs is 0 already we said, right? Means negative voltage. So, so if you want, you can say Vs is equal to 0. You can say if it is less, then what will happen? Then the more holes are attracted, more holes are attracted to the substrate. Substrate connection, leaving a larger negatively charged ion behind. That is simple. I can say what is the meaning of the depletion region is wider. That is the meaning of that. Depletion region is wider. So that is what is happened. So now what will happen? So very important. You may think what will happen in this. So like as the if you want to put the contest in an important point, as if this B voltage is very negative, more and more negative, then the threshold voltage will increase. See, this is what actually, if a bulk voltage goes very less than zero, then threshold voltage will increase. At the same time, if VB goes positive, more positive, then the VTH will decrease. See, you know one thing. Normally, in your MOSFET, the threshold voltage will be set by the manufacturer, adding the doping concentrations. So, due to this bulk voltage, the threshold voltage will get affected. This is simple here I can say. The threshold voltage will get affected. So, I can say the threshold voltage is a function of the total charge in the depletion region. The threshold voltage is a function of total charge in the depletion region. Thus, the body voltage, that is nothing but your VB, that is what the VB. VB will be dropped. Then the depletion charges will increases, which increases the threshold voltage. That effect only we can call that body effect. So the body effect is nothing but what is the body effect here? I can say the threshold voltage. So let us put that is VT, right? Threshold voltage is a function of charge or function of total charge. Total charge in the depletion region. So how can I can say Q dip, I can say. Right. So as the VB drops, that is bulk voltage drops, then depletion, that is QDP, depletion charge will be increases, which increases the threshold voltage. This effect only I can call as body effect. So in practically, if you want to show, you might have drawn some diagrams. I hope you remember that, like in the two input NAND gate. So what is the two input NAND gate? How the two input NAND gate in CMOS it will be like. See, so here This is your validity. This is A. This is B. Same like A, B. But here you are not considered the bulk. So the output will be taken here actually. So for PMOS, always the substrate will be connected to the source terminal. This is the source because for PMOS, always the power supply is connected to source only. Then that is the drain. Now, example I'm saying, okay, so this P for NMOS, always the substrate should be connected to source. For remember that for PMOS, the source is connected to lower potential means, or otherwise I can say VDD is connected to source terminal. For NMOS, the VSS is connected to source terminal. Now you can see this is the bulk. If this bulk is connected over here, we may say, like example, this will be your VA, this will be your VB. Now in this what will happen, your VA will be greater than VTH actually. Here, this point VA will be greater than VB, this voltage. See, because here the bulk is connected to this source actually. When it is connected, that transistor will be in the saturation region. But here you can see, as I mentioned already, always the bulk must be connected to lower potential. See, this is connected, but this is not connected. What will happen? There will be a effect in this place. So this only I'll get as the body effect because that that threshold voltage will get changed over that place. Okay, we need to know one thing. What is the typical value of body parameter? The typical value of body parameter will be 0.5. It is a constant factor. It is 0.5 we can say. Now what we have to do in the sense we need to write from the expression previously we wrote the threshold voltage, right? So from that expression let us write the VT is equal. This is already we know the threshold voltage. PAP flat band voltage plus D by epsilon I 2Q epsilon S NA 2 phi B plus VBS 1 minus e to the power minus 2 beta phi B minus VBS. This will come in the root. This will be in the root plus 2 phi B plus VBS. So now relatively, so the like I said, additional term what we added here in the sense for body effect parameter, you can see this figure actually. This is what, right? 2 phi B plus VB, yes. Hence, we can write relatively the VT voltage, that is threshold voltage, will be obtained from the below equation, that is VT is equal to VFB plus D by epsilon SI 2Q epsilon S NA 2 phi B plus VBS VBS 1 minus e to the power minus 2 beta phi B minus VBS plus 2 phi B. So we'll get the root. Up to here we'll get. Now this will be greater than this threshold voltage will be greater than which we got the earlier equation in the sense in the previous class what we studied actually, because this will increase the threshold voltage when the bulk bias voltage, the VBS, is non-zero, the term that body effect. So VBS is not equal to zero. This is simple condition if you want to say like this. VBS should be not equal to zero, then the effect will happen. That name of the effect is body effect. This is about the effect. Now let us study about the short channel effect. Now, okay, let us see. What are the short channel? But before that, we need to know what is shown by short channel effect. Short channel effect is simple. If the length of the channel goes beyond 1 micrometer, what are the problems will come? As we know that as the length get reduces, so many problems will come, so many effects will be there. In this, we are having some two different effects is there in that. One is nothing but the transistor will be submicron transistor. One is, then second is deep submicron transistor. Okay. Now, submicron transistor. What is a submicron transistor? This submicron transistor is the short channel effect are not so important. Why? Because like if the simple L is greater than 250 nanometer. If the length of the transistor is greater than 200 nanometer, then that we can call the submicron transistor. It is not so important. Means there will not be much short channel effect. So it's not so important. But here, if the L is less than 250 nanometer, means L will be 180 nanometer, 90 nanometer, 45 nanometer, keep on. That is a deep submicron devices. So short channels are so important in this transistor. The short channels are very important. So now here for a given channel doping concentration, the channel length is reduced. Then the depletion layer width of the source and the drain junctions become comparable to the channel length. So what will happen at the time? The potential distribution in the channel now depends on two things. The one is nothing but here, the very important term here I want to say, that is transverse field, or I can call this EX. So this EX I can say nothing but longitudinal, right? Or vertical, I can say transverse field means X, or vertical longitudinal or vertical field. Vertical, that is simple, I can say in the sense it is controlled by the gate voltage and back surface bias. Always we need to remember EX in the sense it is a vertical field. EX is a vertical field. Second, not longitudinal, latitudinal, sorry, okay. This is latitudinal. Second is nothing but longitudinal. Longitudinal field, or I can say E lateral field. Otherwise, that is EY. that is lateral field. Sometimes they may call lateral field. That is, it's a lateral field. What is the meaning of this? This is actually, it will be controlled by the drain bias. Why? Because if you take a transistor, you consider a transistor now. If you are considering the transistor, this will be your N plus, this will be your N plus, then this will be your silicon dioxide, that is a CO2 layer, then there will be metal, here also metal, also metal. So this will be your gate, this is the source, drain. So we are having P substrate, this will be, so this will be your channel. So this is the channel. Okay. Now we have the the depletion region. So this will be your depletion region. So now here two electric field will be there. One electric field in the sense you apply the voltage. One is from gate, like this is the electric field. This is the electric field, starting vertical electric field. I can call this EX. Remember, this is the electric field. Then here one more electric field. Why? Because we'll have the electric field from source to, that is bulk to gate here. There will be electric field here. The one more electric field will be from drain to source. Since the current, right? The current will move from the drain to source as well as from substrate to the gate. That is why. So this will be your EX. This will be your EY. That is the lateral field. That is, I may call sometime E lateral. This I will call as E vertical. So these two terms later we'll talk for each and every second effect. Now let me put a note. The sense like the VT is decreases with L for very small geometrics. The threshold voltage will be decreases with the L, that is the channel length for very small geometry. Means if you keep on, you decrease your L. Say example, if I want to say like for 250 nanometer, the threshold voltage is, say example, 0.6 volt. Then when I go for a 90 nanometer, then your threshold voltage, the threshold voltage here we said 0.6, right? This threshold voltage will be depends on your operating voltage, that is VGS. Say example, if your VGS or VGS will be is equal to 3 volt. So as you studied to calculate the threshold voltage, always it is like 0.2 times of VDD. Okay, so you just to assume as the VDD, VGS is a maximum 3 voltage I'm saying. Same, I will consider this is nothing but VDD. So if it is a VDD voltage in the sense, then your VTS will be 0.6. Now we'll think here for 90 nanometer technology, if I go for as 1 volt, then what will happen? Then VTH will become as 0.2 volt. So as the length decreases, the threshold voltage also will get decrease. So now let us write the short channel effects. What are the short channel effects are there? The first short channel effect is surface scattering. Second is punch through. Next, velocity saturation. Next is impact ionization. Next is hot electron effects. Next will be brain induced barrier lowering. By short, I can call it DIBL, DIBL. Then the last one is narrow with effect. That is narrow gate with effect. Okay, now what we'll do? Let us study one by one. So before that, let me take a diagram. And see, we are showing the cross-section view of mass spect. In this, all things are showing. Like see here, the thing is which we shown. Vs Vb is equal to 0. Then the Vgs is greater than Vt naught. The Vds is greater than Vd sat. So this is exactly, so which region actually? This is the saturation region. You have to remember, you should think like as the length of the channel get reduces, what are the problems will happen? If you reduce, like these are the problems will happen. Like you need to do the, what are the things you need to do in the sense in the second order effect? The one thing is nothing but like you have to do the scaling. The second thing is you have to go for the sub threshold, then starting by the punch through. Later we'll study. Okay, the scaling, actually we are having two scalings are there. One is nothing but the constant field scaling. The second one is constant voltage scaling. So with the help of these two, we can perform the scaling. In the sense, we can change the parameter due to like the L is getting changing, because see here, this full place, this complete is nothing but your L. Okay. Now in the during the saturation region, what happened? The channel will be pinch off. This will be where what changes the del L. So from this only, as I mentioned here, the effective length will be L minus del L. So if it is get reduces, like say here, your depletion region, you can see in the source side. This is your source side. This will be your drain side. You can see the width of the depletion region in the source side is less than the drain side actually. In the normal, in the drain side, it will be more because of this. Now here what you'll do, the first thing is let me go for, or I can say from this diagram will get us like this. Due to that, the L effective will become as exactly as xj. See here, this is the length. This much only will get the effective length. So now let us study about the first effect. Let us study about the first effect. So what is the first effect? The first effect is nothing but surface scattering. Okay. Now surface scattering. So let us see the figure. I need to show the figure for surface scattering. Let me take the figure first. See here. Okay. This will be your MOSFET only. So Vs is equal to 0. Vs is equal to 0. Then your VGS is greater than the threshold because as you know that, so we are operating when you will get these problems in the sun during the saturation region time only. So the surface scattering. So your VDS. So this is the current. So here we can see what happening in the surface scatter. The surface scattering. As the channel length becomes smaller due to the lateral extension, this is your depletion region. See this lateral extension of the depletion region into the channel region. See what happened here comparatively, this you can see this and you can see this. Okay, so now, so as the length of the channel becomes smaller due to lateral extension of the depletion layer. So into the channel region. So the longitudinal electric field component like that is EY, or I can say longitudinal. So EY I'll call, right? The EY component will be increases. The EY is which is EY. So as you know that this is EX, this will be your, sorry, not this electron movement. So this will be your, okay, the movement. So this will be increases as the depletion regions more here. So then the electric field will be increases and the surface mobility become field independent. So now, since the carrier transport in a MOSFET is confined within the narrow inversion layer. So here the inversion layer will be there. So what is the inversion layer will be there in the sense here positive, correct? No, here is positive actually. See here when it is on the positive, how many number of positive is there? That much the holes will be attracted here. So exactly we'll get the mirror of that here. Exactly we'll get the mirror. That is why I can say the channel is inverted. That is why the inversion channel. If it is how much? If it is a 5 electrons, then the 5 holes. So as soon as when it is get, so automatically what will happen? So this will give the way or the channel to move the electron from the source to drain. Then the current will flow from drain to source. So what will happen during that time if the channel is very very small? See, remember the channel is very very less. Sorry, this is the channel example. Okay, example saying this is the channel is long channel. Now this is the small channel. Now what will happen? The long channel is there even though the movement of like a simple I can say you assume as the road. Okay, so for a long road, more number of vehicles if it is going, even though there will not be any collision. But if it is a road is very short road, if the number of vehicles are more, so vehicles in the sense you can consider as your electrons only. Okay, so what will happen? There will be more scattering will be listen, the collisions will be there. Once if it is collision, automatically what will happen? So like it will get scatters. So when it is scatters, this from the surface. The collision will be suffered by the electrons that are accelerated towards the interface by Ex, that is this one. Slowly it will get moved, it will be scattered. So that will reduce the mobility. The electrons will move with great difficulty parallel to the interface. That is nothing but it will be in this Ex vertical field. It will be very difficult to move from the bottom to top. This is what Ex actually. So just I written here. This is what Ex. So that the average surface mobility, even for small value of EY, is about half as much that of bulk mobility. That is what we can call as the surface scattering. Next is we are going for punch through. Okay. Now for punch through, let us go for the diagram again. So this is the one of the effect in the second order punch through. See here in this diagram, I can say this will be your source, this will be your drain. We have the SiO2 layer, then this will be your VG. Okay, now we can see depletion region boundaries. You can see the depletion region here. You can see this electron move from this. So the punch through is nothing but when the drain, which one? This one. So when the drain is at high enough, that is the VDS is greater than very greater than 0 or very high enough voltage with respect to the source, or I can say this one VDS or VD. Okay, VD is more greater than the source voltage. So the drain voltage is more than your source voltage. So then the depletion region around the drain may extend to the source, causing the current to flow irrespective of gate voltage. Essence, even if Vg is equal to 0, even if the gate voltage is 0, then there will be a current flow. That is known as surface punch through. Surface punch through as it takes place away from the gate oxide. This is your gate oxide. You can see because there will not be any direct current flow between the gate and the substrate actually, right? So your drain, you see, this will be your P substrate. This will be your bulk. So when the channel length L decreases, the punch through voltage rapidly increases. So now the channel length L decreases in the short channel length case. Okay, if the channel length is decreases, then punch through voltage rapidly increases. So in the short channel device, due to the proximity of the drain and source, the depletion region at the drain and the source, depletion region at the drain and the substrate, because your the depletion region will never touch the body. As you know that you will get the depletion region like this. You can remember the previous cases. Okay, so depletion region will go this will be to your source side, this will be in the drain side, but this depletion region will never touch the body. Keep it in the mind. So that won't touch actually. So the depletion region at the drain substrate and the source substrate junction extended into the channel. So now as increase in the reverse bias across the junction also pushes the junction near to the each other. So now when the combination of the channel length and the reverse bias leads to the merging of depletion region and punch through. Yes, sir. This is the merging. See here, this is what I said here. Okay, so these two places only can call us the depletion region, the boundaries. So this is what we can call as punch through. Next is nothing but next parameter, or I can say it is nothing but a velocity saturation. Now, what is the velocity saturation? Remember that in your MOSFET, as I mentioned, two field is there. One is the lateral field and the longitudinal vertical field. That is X and Y. So the voltage applied between VDS, that is that side EX I can say. Another one is EY we can say. Now we can remember that the performance, the short channel device are also affected by the velocity saturation, which will reduce the transconductance, that is GM in the saturation mode. Next, as the electron drift velocity in the channel varies linearly with the electric field intensity. So if you want to say, let me take a example as like this. Say, let's say write E lateral. Okay. So E lateral will be is equal to VDS by L. What is the lateral? The E lateral is nothing but E vertical. That is nothing but X. Okay, EX. Now, E lateral is something VDS by L, where the VDS is something by the voltage across the drain to source divided by the channel length. That is something X-axis only. This is the X-axis. Okay. So now we can say, what about the electric field vertical? That is E vertical will be, that is the vertical side. VGS divided by TX. Why? Because, so we can see here, n plus P, then this will be your channel length, okay, L, then this will be your silicon dioxide, that is thickness will be Tx will be there, then this will be your gate, this is your source, this will be your drainer. Now that is the first I can say E lateral. The E lateral is nothing but this only, right? Okay, E lateral. This will be your E vertical. So VDS, the voltage across VDS divided by the length. So let me show the relation, how it will be. Next, if I say the E vertical will be VGS, because we need to apply the voltage between gate and source divided by, there will be a barrier over there, that is nothing but the Tx is there. Okay. Now we can see here what will happen. Simple logic. Okay. As the L length is decreases, remember that. What will happen? As the length decreases with the constant of VDS value. Just assume as the VDS is constant. If the VDS is constant, the L is reduces automatically. What will happen? The electric field? Electric field will be increases. Correct? As a simple relation we can say. As the channel length is get reduces when the VDS is constant. When VDS is constant, then what will happen? Your electric field will be increases. Now let me talk about with in terms of little bit like same I can say if the VDS also will be increases. Sometimes like constant or you have to increase the VDS automatically E letter also will be increases. Okay. Now let me go for with respect to because VD that is the drift velocity. Drift velocity, the relation will be like this. Drift velocity will be mu into E. Drift velocity mu. Mu is nothing but the mobility, right? Mobility. E is nothing but your electric field. What is the drift velocity? What is the meaning of the drift velocity? How fast the electrons will be sweep. That is what we can say here normally. Here velocity in the sense, simple I can say, how fast the electrons will move from source to drain. So that will be based on the mobility. So that is the based on the mobility in the sense of VD I can say here. As the electric field increases, simple right? As the electric field increases, automatically I can say the drifting also will be increases. So next I can say with respect to lateral field also VD is equal to mu into E I written. So we have to talk about the E lateral. So simple as the lateral electric field is get increases. When this lateral electric field increases, as the L is get reduces, then the electric field will be increased. If the electric field is increases, then automatically the drifting velocity also will be increases. It will go to the saturation. That is what, as I mentioned here, at like this is we can called as velocity saturation at one particular point of the time. Your channel will be pinched off because velocity saturation means what? How fast the electrons will be moving. But one particular point of the time that will be saturates. That is what we say here. It is the velocity. So now from that, we can make a note of that. In this condition, we can make a note of that. Note the drain current is limited actually, right? The drain current is limited by velocity saturation. Velocity saturation instead of pinch off. So this will occur in the short channel devices when the dimensions are scaled without lowering the bias voltages. Now to using the VDS SAT, we can find the maximum gain. VDS SAT, we can find the maximum gain. The maximum gain will be denoted as G max. G max. So G max will be is equal to W into Cox VDS into SAT. Because as I mentioned here, this is the formula to calculate the maximum gain. We can calculate W into Cox VDS. This is called as alternative. Now from this, one thing we need to know, like how much the electron will be there. Like I need to show, like you may ask how it will be there for long channel effect and the short channel effect. Then what about the current also? So let me show some graph. The first graph which will be shown as here. So this will be a long channel effect. This will be a short channel effect. So here I can say this is IDS. Now we can see here this is nothing but your VDS set. Then this portion is nothing but I can say VGS minus VT because this is nothing but a VDS. This will be your long channel. This will be your short channel. You can see here IDS. You can see there is a comparison. Like in the short channel, actually, this two you can say. This is VGS is equal to VDS. Your dryness get reduces, right? Long channel. This is for short channel. See, very much different will be there. But at the same time, if you want to show there one more graph. I'll show the one more graph. See this? Like I will say the maximum velocity here. This one is V sat, right? V sat will be 10 to the power of 7. This velocity will be centimeter per second. So I can say in this above this V sat, this portion is 10 to the power of 5. So V sat is 10 to the power of 5. So this portion is after this will get a constant velocity will be there because as I mentioned at a particular point of time there will be constant velocity. Then here we'll have the if it is constant velocity then constant mobility. So that is why we return as like this. V is equal to mu E. So very simple, we can put a condition as like VDS by L is equal to, if the VDS is 1 volt, then your L is nothing but example is 20 nanometer, then your E lateral will be, because this is E lateral, correct? Then your electric field will be 5 into 10 to the power of 5 Weber centimeter. As you know, the drift velocity Vd is equal to mu into E lateral. The V is nothing but the mobility of the electron multiply with the E lateral will get. That is what the value. So in this way, we can calculate the velocity saturation. Next parameter. The next parameter is second order effect is impact ionization. So the impact ionization, it is a process. Let me write. What is the process? Process is a material by which one energetic carrier can lose energy by the creation of other charge carrier. From the name only we can say impact ionization. It will be like ions, it will be ionized. That is the one thing simple I can say, because we need to consider BJT and MOSFET. Let us take that only is the example here. Next thing is here, we need to say the impact ionization is nothing but what? It is a process in a material, sorry, in a, it is a process in a material by which one energetic carriers can lose energy by the creation of the other charge carrier. So now here, this short channel effect, this impact ionization effect, especially in NMOS, it will occur due to high velocity of presence. So this I can say the condition is like this, I will say. So this will occur due to the high velocity of electrons in presence of high longitudinal fields that can generate electron hole pair. Electron hole pair by impact ionization. So it will like by impacting on silicon atoms and ionizing the. So it will happen as follows. Normally, the most of the electrons are attracted by drain, while the holes enter the substrate to form the part of parasitic substrate current. Moreover, the region between the source and drain can act like base of the NPN transistor. So as you know that in BJT, how many terminals are there? In BJT, NPN transistor, we are having that collector, emitter, and the base. Same the way, if I say the FET, what I can say, this collector will be drain, this emitter will be your source, then the base is nothing but a gate actually. So simple I can say like NPN junction in the sense this is N P N. See, it will be like this N P N. Now what will happen here? We are having a two barriers. See here, there is a barrier, one barrier. There is a one more barrier over here. Correct? So two barriers are there. See in between. So we need to analyze. So now that is the reason here you can say like the drain can act like a base of the NPN transistor, with the source will be playing the role of emitter and the drain that of the collector. The holes are collected by the source. The holes are collected by the source, and the corresponding the hole current will create a voltage drop in the substrate material of order 0.6 volt. The normally reversed bias substrate source PN junction, because this is a reverse bias, right? Reverse biased substrate PN junction will conduct appreciably. So now the electrons can be injected from source to substrate. Electrons will be injected from source to the substrate, similar to the injection of electrons from the emitter to the base. So they can gain the enough energy as they travel towards the drain to create a new electron hole pair. So this situation can worsen if some of the electrons will be generated due to the high field that will escape the drain field to travel into the substrate. So therefore it may affect the other devices on the chip. So here what will happen here, sometimes the electron may have very high kinetic energy. So let me show with the impact ionization with that diagram. I'll show the diagram. See, this is your electron. Okay, this is the electron. So here we are having the electron hole. Like example. Okay, so here I can say this will be your conduction band. This is your valence band. Now what will happen? This has which one? This electron has very high kinetic energy. Very high kinetic energy. So this is the energy. Okay. Kinetic energy. So automatically what will happen? So if it is very high kinetic energy, then so now the high electrons will be transferred the energy to one electron in valence band, prompting to the conduction band. Now at this time here what will happen? Here in this valence band, the holes will be created at the time. The holes will be created due to the absence of electrons in the valence band. So that is what is the impact ionization. Next is hot electron effects. Hot electron effects are sometimes we may called as hot carrier effect. Okay. Now what is this? This is one of the another problem in the short channel related to high electric field. So it's related to high electric field, so caused by hot electrons. So those high energy electrons can enter the oxide where they can be trapped. So giving rise to oxide charging that can accumulate with time and degrade the device performance by increasing the threshold voltage, and it will affect the gate control on the drain current. So because these things, same example we need to consider here, the drift velocity, that is Vd, will be directly proportional to kinetic energy. First, kinetic energy. So because the kinetic energy is very high, that will make the electrons make hot. So how it will happen? This one same. Even this also will may happen from the E lateral. As we know, the expression E lateral will be is equal to VDS by L. Then E vertical is equal to VGS by Tox. Then what will happen if your L is you are doing the scaling? Okay. when you are doing the scaling, then I'll say E lateral is equal to S into VDS by L, where the scaling parameter, the new L is nothing but L by S. L dash will be is equal to L by S, where S is a scaling parameter. S is a scaling parameter. Okay, so now as the VDS gets increases, electric field also will be increases. Then we can say what is the drift velocity? The drift is Vd is equal to mu into E lateral. As the E laterals get increases, then the drifting velocity also will be increases. If the drifting velocity is increases, then automatically I can say simple your VDS, that is what is the meaning of that? What will happen? When VDS, the drain to source voltage will be very much greater than VDS SAT. So in this, the channel will be pinched off. The channel is pinched off. The channel is pinched off, then automatically what will happen? Like the high energy electrons, the high energy electrons will enter into the oxide because the electrons will be moved from the source to drain. The channel is pinched off. If the channel is pinched off, automatically what will happen? Because of due to that, that will enter into the oxide also. If it is get inside into the oxide, your oxide layer will get damaged. If the oxide layers get damage due to why because it will get more and more electrons are passing, so it will have more hot will be there because of the electrons will make more hot, so it will gives rise to oxide will be charging because of if it is because that will be accumulate more and more electrons are accumulated over there, automatically what will happen, like it will take it will be charging that can accumulate with the time, so that will degrade the device performance by the increasing threshold voltage. Due to that, the threshold voltage also increases. So let me show like the diagram for hot electrons. See here, you can see we are showing the diagram here. Source, see, that is electric minimum will be greater than the, that is E, right? E minimum greater than the kinetic energy. So as I mentioned here, see here, because of the channel, see, this is the channel is pinched off, right? The channel is pinched off, what happens? It's moving to the oxide, then the oxide will get damaged. If it is get damaged, then so there will be increase of VT, and it will affects the gate control because the gate control on the drain current. That is nothing but hot electron effect. Next parameter is drain induced barrier lowering. That is by short, I can see dibble. What is the dibble here? So same now again for dibble also what we have to do in the sense, two things we have to consider. Like the expression, let us say the expression for for the drain and source junction with source junction with will be written as like as XDD. Okay, XDB will be is equal to 2 epsilon Si divided by QNA VDS plus ISI plus PSB. Next is XDS. Okay, depletion region of this one. So XDD, this is not DD, this is DD, is equal to 2 epsilon Si divided by 2 Na pi Si plus PDB. So here where the VSP is nothing but source to body voltage. So VDB is nothing but drain to body voltage. Now here, see here, very simple. There will exist a potential barrier between the source and drain, which is to be lowered by applying the gate voltage. In short channel devices, in addition to the gate voltage, the drain voltage also will become a significant effect on reducing this barrier. So now as the source and the drain get closure because of short channel, the source and the drain will get very closure. So if it is comes very closure, then it will become electrostatically coupled. If it is electrostatically coupled, so that the drain bias can affect the potential barrier to carrier flow at the source junction. As a result, the sub-threshold current increases. So what is a sub-threshold current? You need to know. What is by sub-threshold? So sub-threshold is nothing but it's a less than threshold voltage. As we know that VGS is less than threshold voltage, then so we may say it will be in the cutoff region. Means so the transistor is in off. But when you are increasing the VTH or when you are increasing your VGS value linearly, like say example 0.1, 0.2, below that there will be, but logically I can say it is cut off in the 0 volt. But practically if I talk, it is not 0 volt. There will be small amount of voltage will be there or the current will be there, that in terms of the PF, the ID. Okay, that is why I can say the sub-threshold is less than threshold voltage. So for these things will be work for submicron devices. The submicron devices will work in the sub-threshold. So like which are the devices are operating in the low power devices, low power circuits. So for that and all, we need to operate with the sub-threshold condition only. So that is why I can say then the source and the drain get closer, then it is electrostatically coupled, both source and drain, so that the drain bias will affect the potential barrier to carrier flow at the source junction. As a result, the sub-threshold current will get increases. As the drain depletion region continues to increases with the bias, then can actually interact with the source to channel junction and hence lowers the potential barrier. So that problem only we can call as drain will induce. See, the drain will induce the barrier, the lowering. That is why we can say normally we're compared to the width of the drain region of source will be larger than the width of this uh, drain actually. The depletion region width in the drain side will be larger than the source side. Right, so the drain depletion continues to increase with the bias. They actually interact with the source. So when the source junction barrier is reduced, the electrons will be injected into the channel, and the gate voltage has no longer any control over the drain current. But some of the long channel devices, the source and the drains are separated the far enough distance. The depletion region will have no effect on the potential, or there is no effect in the field pattern in most of the devices. Hence, for such devices, the threshold voltage is virtually independent of the channel length and drain bias. So here, so let me show the diagram for Dibble. Like the Dibble diagram will be, and see this.
Here we are showing both.
So here we are showing the long channel also. Then we are showing for short channel also. We can see this for long channel. This will be your depletion region. See here the depletion region. See this. At the same time, you see the distance between source and drain. But you can see if I take a long channel, this is source, then this will be your drain. See how much the distance we are having. So it is not electrostatically coupled. But in the short channel, it is electrostatically coupled. When it is electrostatically coupled, then automatically there will be a drain depletion region will continues to increase with the bias. So you can see in this the position along the surface of the channel. This is electron potential energy. This will be electron potential energy. So this will be your long channel. This will be your short channel. You can see this. So this is what I can say. Double. So drain will be induced barrier the lowering. So in this portion, the Vs will be is equal to 0. This is your drain voltage. See this drain voltage. So now we can say from this point, the double, this double is enhanced at high drain voltage. High drain voltage and shorter channel length. Here, simple we can say when source and drain later depletion with approaches the channel length, that is the punch through occurs, then the large leakage will be between the source and drain. The next thing is the majority carrier from the source will be injected into the channel. So it will be swept by the field, that is collected by the drain. Then the VD lowers the VD, that is drain voltage, lowers the barrier near the source. This only we can call as Dibble. This is about Dibble effect. Next, the last effect is nothing but last second order effect is narrow width effect. narrow width effect, or sometimes I may call this, it is nothing but a sub-threshold voltage also we can call, or due to the sub-threshold. Narrow width means you can see, now here we have to think uh, like W by L ratio is the right. Still now we said the L is very small, correct? No. Now just make a reverse of that. Narrow width, the width is very, very small. Now whatever the diagram we drawn, so for that, so just a simple, I can say the diagram. So this will be your general diagram. This is the L, right? This is the L, this is G, drain, bulk. Now you can see from the top how it look like from the top actually. This will be your channel length, correct? Then we'll have the width. Width will be like this. We'll have the width of the channel here actually will be. Now just from the top you make it the inverse of that. The sense your width of the your width is this. This is the width. Okay, this is the width you see. Your length is this. This is the width. Now, if it is happen like this, just it is a imaginary visual you have to make. In the visual, just to make it narrow width in the sense like your width of the transistor is very, very narrow. Like I can say, comparatively, if I say in the earlier cases and all, your W will be larger than length, right? So, like a simple CMOS structure, if I take any simple CMOS, normally your width of the transistor will be normally like equal ratio also we may take, or we may take ratio like say example 4 is to 1. Your length will be 4, your L will be 1. We may take. Now it's a very narrow, in the sense equal or less than that, equal ratio. Anything you can say. So in this time, if the MOSFET is narrow with but the VT, that is the threshold voltage, will increase as the channel width, is reduced for reduced for reduced for very narrow devices. Disha Kiran, so the threshold voltage will be increases as the channel width is reduced for very narrow devices. So some of the depletion charges will be under low cost, that is local oxidation isolation region. So I think in your various you might have studied, one is called as low cost region, another one is called as shallow trench isolation region. So these two are will be used for your SiO2 actually. So here we can say simple. This effect is not that much important actually, but it's quite important as width are reduced less than 1 micrometer. It's quite important when it is important as the weather reduced below 1 micrometer. So if the W is reduced 1 micrometer, then this issue will be viewed as very serious. The second thing is we can say that the depletion charge will be reduced due to charge sharing. Due to charge sharing, actually, the effective depletion region is reduced due to charge sharing. Due to charge sharing with the source or drain. So here the depletion charge belongs to the gate is increased. So let me show how the diagram will be there for narrow width effect. The diagram for narrow width effect. See here, we're showing this is nothing but your channel width Z only. Channel width. So now the diagram is made of reverse, right? Okay. So this is the channel stop implant. So now you can see this will be your channel width. This will be your channel length also I can say. This additional depletion charge. This will be your thin gate oxide SiO2 polysilicon. So this is what I mentioned over there. If this is less than, so if I make less than that, okay. So if I reduced this one, if I reduce to this one, so these are the problems will happen. This is one of the um, effect in the second order, or I can say it is one of the short channel effect. But as I mentioned earlier, it is not so important effect. It's somewhat when it will be important. This is when your the width gets less than 1 micrometer. I hope you might have understood. I think it's clear for you. Okay. Now let me put something for you. I need to tell something about your internship. Some of the queries in the sense made earlier. Things that keep it in your mind related to the internship. Okay. So those who are done the internship during the period of your sixth semester, even though if it is an online internship or offline internship, so that is welcome. So you can submit the certificate. That is also will be acceptable. Second thing is you need to start your to do your internship. You don't wait for the college will give you the green signal because unofficially I'm telling you unofficially to start because still we didn't get any information. So you start your internship. The internship, the period of the duration will be 90 hours. So you think about if it is 90 hours, if you are doing internship per day, the complete 8 hours, then it is 2 weeks. 2 weeks internship. So, or 3 weeks internship or 4 weeks internship, but it's supposed to be you have to meet 90 hours. Then, so you need to complete your internship along with the report. You need to prepare all these formats, everything I sent to your mail. Then you need to complete your internship before the uh, March 15th, I can say before the March 15th or before the March end. Yes, before the March end, you need to complete your internship. Those who are waiting or those who are looking for the which one the letter from the college officially, if you want for an internship, that you can get it after March 15th only. You will get, or you can come and approach like where you want to do. So meanwhile, so many internships are available by online also. Even you can do there also. Then one more thing important. I don't want everyone should go and accumulate in a same company. So the maximum of two members or three, maximum of two only I can say. Worst case only three. One, the two members can do in one company. Then I don't want everyone has to do in same field also. Just so many diverse fields are there in electronics, so you can choose that diverse fields. So many field is there. Either like communication is there, signal processing, DSP is there. Then you can do in the image processing. You can do in the VLSI. You can do in the biomedical applications. So many things are there. So you have to choose. So like in which uh, the domain, the area of domain you want to do the internship. So you can do the online internship also, but simply don't get the certification because, as I said, you are having a examination. Seminar examination also is the. You need to prepare your report. You need to prepare a presentation. You need to explain. You have to submit the weekly report also. That also I will send you every week the updation you have to do. So it is a individual. It is not a group actually. It is individual. Then every person will get a guide. So by shortly by today or tomorrow, I will send the internship guide also. So meanwhile, if you are doing a internship in so and so company, update with your guide also. So this guide is different from your capstone project guide actually. So don't think about the same guide. So not the same guide, you may get the different guide actually. So to for your internship with respect to the internship. So still, if you are having any more doubts in your internship, then don't hesitate. You can contact us. Second thing is I want to say, as I mentioned earlier, so many n number of times I inform to you people to appear for the KSCSC, the project fund proposal. I since still none of the batches are take forward. So only one batch they said something like earlier meeting, one or two batch they given the reason, but I doesn't know about the other batches. So even if your project is well versed with if you are having in that team, then better just you can apply. That will give you more benefit for you in the sense like then you can build your resume in good way, so there will be some good reputation also will be there for you if your project is selected and if you get any funds. So just still, as I said already, I mentioned, I insisting you people try to give within this week, within this week. So keep on, I'm telling, but none of the students are not responding for that KSCST. Is there any issues are you facing related to KSCST?